bachelor's and master's degree from the University of Coimbra, Portugal, and did his PhD at Princeton under Amit Singer. And he has been a faculty at the Mathematics Department of the Courant Institute of Mathematical Sciences, and was part of the Center for Data Science there. This is the center started with co-founder like Jan LeCun, right? And then he moved to Zurich last September. And he's generally interested in research around mathematics of data science. And he's I would say, in our generation, he's like our Messi. He has won a lot of recognitions. The Sloan Fellowship in 2018, the 2019 Isaac Prize for Young Scientists, the 2020 Stefan Mail Prize from the FOCM Society, and the 2020 Information Theory Society Paper Award, just to mention a few. So we look forward to his wonderful talk. I just wanted to say a few things about housekeeping rules. Everybody should remain muted while the talk is going on, both video and audio. You can ask questions on the chat while the talk is going on, but if you just also want to ask questions, you can just say it on the chat, and I will unmute you, and you can. Alfonso doesn't mind you interrupting him while he's talking, so you can interrupt and ask questions. Actually, he encourages that. He wants you to ask questions while he's talking. So just say you want to ask a question on chat, and then I'll unmute you, okay? And yeah, so no screen share also. Previous seminars, some people mistakenly try to share their screen. So please don't share your screen, okay? This will interrupt the screen share of the speaker. Okay, Afonso, you take it on from there.
Right. Thanks so much, Abubakar, and yeah, thanks for the invitation. It's a pleasure to give this talk, and thank you all for coming. So I'm going to give a very overview talk and very high level, but I'm happy to get into any details if someone is interested. So, if you have questions through the talk, just ask them, and in the end, I'm also very happy to just go deeper into some of the topics if a particular topic interests any of you, and I'm happy to even go on the board and just describe things in more detail and more technically. Okay, so I'm going to talk today about computation, statistics, and optimization random functions. The idea being that some of these things are related, and I'll try to convince you why and how. And first, let me just give this probably is not really needed, but maybe it's a good starting point nonetheless, of just for us to realize the importance of data these days, right? So I could give some statistics on how many clicks are there on Google per second and things of this type, but I think everyone by now realizes that these numbers are just all massive. And so instead, I decided to pick some cartoon pictures that I thought were just very, very clever, right? And one is, there was this title in The Economist saying that the world's most valuable resource today is data and no longer oil. And I saw in another place an estimate of how much data, or in particular AI-powered applications, which basically means data-powered applications, how much they're worth and how much they bring in value to the global economy, and these were just massive numbers. They're big percentage of the value of the total value of the economy, right? And I thought this cartoon was also quite clever of how our data is up for sale in a certain way, right? And it's not. I mean, here there's like a bid happening in this cartoon, and there's some numbers, but it's actually not quite clear what the numbers are really, or even how to evaluate them. In part because it's not completely clear what it is that you can do with data and what it is that you can't, right? And so this is sort of a very central question that I'm very interested in, is what is actually possible to learn from data, what isn't, and what is difficult about learning, what is easy, and trying to understand it from a very fundamental viewpoint. And so just because, when you think of data, you probably think more of this picture of data as in like you're in some social network and you're producing data. But there's other examples, much more sort of classical looking in a way, where the improvement of algorithms that learn from data has also brought a big progress on things that are much, much more classical in nature. So one example that is very close to heart, because I've worked a fair amount on it myself, is cryo-electron microscopy. So let me just give you as an example that's sort of very different from the usual examples that one sees in machine learning, right? But a very important example nonetheless, in which, so here you want to know the 3D model of a molecule, right? So you have, right, depict there, I don't know if can you see my pointer or no?
Yeah, you can see it, yeah.
Okay, great. So you can see here, there's like the little molecule, which is some kind of cylinder that you see. And what you do is you freeze this molecule and you take an electron microscope, you just shoot electrons, and some of them get trapped in the molecule, some of them make it through. And so essentially you get a shadow on the bottom. You get some shadow on the plate. Right? And now the problem is, from this shadow, can you recover the structures? Now the problem is that these are complicated molecules. You don't know how to tell them to pose for the picture. And so for each one of these, you actually don't know either what the molecule looks like, or what rotation the picture was taken from, what angle, what viewing direction the picture was taken from. And this really causes difficulty, right? It's almost like a chicken and egg type problem. Really is one where if you knew one thing, the other would be easy, and vice versa. And so very prone to like alternative minimization type methods and so on, right? And so, if I get some pictures from the lab, right? These are pictures actually from the lab. I can't even tell that there's something there to start with. I mean, the level of noise is just so high, right? And usually when we think of machine learning, we don't think of, improvements in algorithms learning from data where there's this amount of noise, right? I mean, here there's really, you can't even, if you squint at it, you can kind of see that there's a lighter part in the middle, but it's quite hard to even tell if there was something there to start with, right? The level of noise is just insane. And so because of progress, both on the microscopes themselves and the sample preparation and so on, but also very much on the algorithms, this has improved immensely, right? So before 2013, here's a protein, and you see, right? So this is a depiction of how well you can now resolve things. You see, before 2013, you could get some blobs. I mean, it's still pretty impressive that you can get some blobs. But if you look in the present, you start seeing all sorts of interesting, biological structures. Right, it very becomes much, much more useful, right? Because now that if you can see biological structures, you can understand how it interacts, what you could produce to have it interact in different ways. I mean, right? The potential is enormous. And in fact, this won the Nobel Prize in Chemistry a few years ago. Okay, so now let's go back to more general terms. I just wanted to sort of mention both the more usual applications when one thinks about data and the revolution of data and so on, but also some more classical ones where you definitely see improvements. And as a mathematician, and in particular as a person who's interested in theoretical side of things, what I'm really interested in is understanding what are the limits of what one can learn. And are there limits, right? What can I say is things that I can't learn, or at least with a certain amount of data I cannot learn. Right? Which methods work and why? Right, and for this, I picked also a very clever cartoon from XKCD, as they usually are in XKCD, where I'll let you read it. But right, this person says they have a machine learning system, and they say, okay, so what you do are you put in the data and it takes out answers, and they say, okay, so what if they're wrong? You just stir it again and try again, right, until they start looking right. Okay, so of course this is a caricature of reality, a very strong caricature. Nonetheless, if the methods that work very well in many problems, they're based in deep learning and neural networks. I mean, a pile of linear algebra is maybe too much to say, but they're certainly based in linear algebra, and you don't just stir the pile, you train them. And a lot of thought and a lot of technology and sort of evolution of what we understand of deep neural networks has gone into training them. But you do effectively train them until the answers start looking right. And it's fair to say that we're still a little far from understanding exactly why they start looking right. So we don't quite understand exactly yet why they work. We've made a lot of progress, I think, in the last, say, half a decade to a decade, but we're still a little far from understanding really why they work. And in particular, I would like to understand, what are the bottlenecks? What are the difficulties to learning more? And something that's not maybe discussed as much, but I think is quite important, and I would like to mention it a little, is can we have some kind of a posteriori certification, right, of being sure, or evaluation of how good our answer is, or what we learn, make sure that we actually sort of learn the right thing, or the answer that we have, can we give some kind of quality control to it after the fact? And I'll try to give a few examples. Okay, so if you ask now the question, okay, so what is the limits of learning, right? So if we're trying to learn a task, how can we say that, yeah, we can't learn it any better than a certain amount? I mean, one place in knowledge, I guess, where this has been discussed already goes back to the 1700s, right? In the work of a lot of the people responsible for the creation of statistics and a lot of the methods there. The idea being that in Bayesian statistics, you already have this notion of uncertainty, right? If there's a parameter that you want to learn, you have a notion of a posterior distribution of this parameter, right? And so this gives you a notion of uncertainty, right? Because if this posterior is very concentrated, you have very little uncertainty. If it's very spread out, you have a lot of uncertainty. So it's already implicit here, you know, thinking about this was like a few centuries ago, and there's already a notion of uncertainty in things you're trying to learn, right? Learning here is posed in terms of estimating a parameter or inference, but it's learning nonetheless. Right, and if you go forward 200 years, you get the notion of things like Fisher information, which effectively are telling you how much, I mean, in a way, how much information is there about a parameter you want to learn on a sample that you receive. Right, and this is clearly getting at the point of, then you can start hoping to ask questions, how many samples do I need until I have enough information, right? You start being able to ask questions of this type, or at least hopefully. Right, and the idea of Fisher information, I tried to actually do my homework and go see where, you know, who had this idea before or in which form. And what I learned is that there's not a total agreement on who had this idea first. Let me just leave it at that. Right, then you start having very precise statements about limits of a certain type of learning, which is hypothesis testing, which is actually one of the simplest, which is I only have two possible states of the world. There's only two possible possibilities, right? One, the world, what you see, the data comes from a distribution A, the other from a distribution B, and you just have to tell me which one it came from, right? And Neiman and Pearson, the Neiman-Pearson lemma tells you sort of exactly what are the limits to this, right? How good can you get in terms of false negative, false positive rates, and so on, right? And then if you go forward and so on, you get things like the Kramer-Rao bound, which is giving lower bounds of how good an estimator is, and then things more sort of more sophisticated things in terms of more asymptotic, in terms of minimax type methods, contiguity, and so on and so forth. Right, there's another side of this coin, which is on the information theory, which in a way also measures, you know, how much of information is there in sort of measurement in a way, but in particular, there's this notion of how many bits of information do I need in order to identify a draw of a random variable, and this becomes crucial when trying to understand when is it that I can actually infer a parameter or learn something. And so this is due in big part to the work of Claude Shannon and Richard Hamming. It turns out that they were actually, you know, geographically quite close. They were in the same, at some point I think they either shared an office or in next door offices. And they created theories that are, you know, they're not the same theory because they were interested in different things. So Shannon was interested in communication and making sure that if things in a communication channel got lost, maybe, you know, randomly, that things would still be okay. So you have enough redundancy for that. While Richard Hamming, as far as I understand, he was running big computer programs at the time where the input to the computer was given by a pad with little holes on it. And sometimes the computer would read the holes incorrectly. And so he wanted to, and the story goes that he once lost like a week or something like this of computer time, or a weekend or something, because the computer made a mistake in the reading. And so he wanted to come up with an encoding such that even if the computer got a few of the holes wrong, it would still be able to read it correctly. This is then give rise to these error correcting codes and all this stuff, right? So it was more like you wanted to be able to handle any kind of perturbation, while Shannon's perturbations were more random, but the theories were actually quite similar. Right? And if you, as you can see, they're around the same time as well. Now, okay, so now this tells us this work up to, I listed work up to the 50s, maybe even 70s, of many different areas of knowledge, or at least, you know, different views of how can you try to measure how well you can learn, or how well you can infer, or how much information you need in order to make some decision about what is the right parameter, and maybe how much information you get from each measurement, from each piece of data. Okay? But even if you push that kind of path all the way to its end, what you're going to be able to say is maybe there is enough information in the data for me to learn what I want to learn. Right? But that doesn't mean that we can do it. Right? And so let me try to just convince you that maybe that doesn't mean that just because there is information there that we can actually learn. And what I want to note is that learning is oftentimes also optimizing, right? Because when you're doing estimation or learning, almost always you're trying to find a parameter or a signal or a model that best fits the data, right? So, right, you can come up. There's many instances of this. Maybe the ones you should keep in mind is something like maximum likelihood estimation, right? You come up with some model and you find the parameters that maximize the likelihood, right? Or you come up with some model like a neural network and you try to find the parameters that minimize the loss, right? Or you train it locally to find locally the parameters that minimize the loss. But in the vast majority of instances, you have some type of model. And what you do is you try to find the parameters that sort of have the best fit or less loss in this model. Okay? But now you could ask yourself, okay, so now I have a really good model, really good data. I know that if I can find the best, optimize the model, then I'm good. But that doesn't mean necessarily that we can optimize the model. Right? Optimize the model might be a very difficult problem in itself. Right? So it might be that we have the right data, the right model, but now we can't optimize the model. Right? This is definitely a risk that we need to understand if it's the case or not. And there are many problems that are known to be difficult. Right? So one, there's many classical examples. A classical example is knapsack. Right? So the problem here is you have the trunk of a car, you have many bags, and the question is, can you pack the bags and still close the trunk? Right? And so, if you just have a few bags and their shapes are kind of nice, this is not so bad, but you can imagine how this can get quite complicated. The shapes are very complicated. All right, and in particular, this problem is known to be NP-hard. Right? What does it mean to be NP-hard? I won't go, there's no need to go in the precise definition, but essentially means that it's very unlikely for there to be an algorithm that can solve all instances of a problem of this type. Now, one important thing that NP-hard problems have is that it's usually very easy to check a solution. If someone proposes a solution, it's usually very easy to check it. If someone attempts to pack the trunk of the car, for me to check whether it's an okay solution or not, all I have to do is to try to close it. If it closes, it's fine. If it doesn't, it's not, right? So the task of checking is very easy. And usually that's the case also in the problems in learning, right? Because at least from the viewpoint of the optimization problem, if I'm given parameters, I can easily compute the fit and the loss and so on, and I can see if it's a reasonable one or not. Now, if this notion of are there problems that are difficult, right? That are inherently difficult, or do we believe? I try to trace it back by doing again my homework, and essentially gets, as far as I could see, gets traced back from by a letter that Gödel wrote to von Neumann in the mid-50s, where he asks about whether a certain problem, I think was some form of satisfiability question, might be that it needs, I think he asks if it might need quadratic time, if it might be that it's impossible to solve this problem in linear time on the size of the data. And there's also a letter, I think, from John Nash maybe to the NSA or something like this. I think this, if you look at this, is available. And where he also is more interested on the cryptography side of things, but he asks a very similar question. And interestingly, right, these people were all in Princeton around this time, so it's kind of clear that this question was floating around in the mid-50s in Princeton. And now, if you go back, if you go forward like 15 years, then the very important seminal work of Cook and Karps, they basically defined NP-hardness. Basically, what they did is they found a set of problems, and they showed that they were all as hard as another. Right? And these all problems were NP-hard or NP-complete, and if you could find an algorithm for one, you could transform it into an algorithm for any other. And because we've tried for many years and have not found an algorithm that works for any of them, we sort of believe that this is actually, there is no such thing as an efficient algorithm for these problems. Okay? Now, okay, so we see this two sides of this story where we have the statistical or learning problems that give rise to some kind of optimization. And then we see that many optimization is clearly a computational problem. We see that many such problems actually are NP-hard. So what makes sense? It makes sense, well, okay, so when I design my models, I should just design my models in a way that it makes optimization be an easy computational problem. Right? This is a very natural thing to do then. Right? If it was many years ago before computers and I was trying, then probably didn't matter very much the computational complexity of this. Now it certainly makes sense that if I'm trying to come up with a model, if I want to actually use it, I better come up with a model where optimization is easy. And this is, in a way, the reason why, when you're learning things, linearity, convexity, and all these things show up so much, right? Because they tend to give rise to optimization problems that actually we can solve, and we know that they're not NP-complete, or we know that they're easy. Okay, so maybe I'll give 5 seconds or 30 seconds for someone to give the opportunity for someone to ask a question, because this is a good point. If something is not clear, I'm going to give an example now. I can't see the questions myself, so if there's one, Boubacar, please just ask.
No questions on this chat.
Okay, yeah. So I'll go into, thank you. So I'll go into an example. Okay, so here's one, another example close to heart. This is the problem of determining communities in social networks. Okay? And under because we want to do precise mathematical understanding of these problems, I'm going to come up with I'm going to study a very precise generative model, right? That dates back actually a few decades. So let's draw a random graph, right? This random graph will have n nodes. And now I split these nodes n over 2 to the left, n over 2 to the right. Okay? So half of the nodes I color blue, half of the nodes I color red. And now I'm going to draw edges in between these nodes. If they are, all edges are going to show up independently. And if they are in the same color, they show up with probability P. If they have different colors, then they show up with probability Q, right? And I make Q smaller than P. Now, this graph clearly has some form of community structure, right? If Q is very small and P is very large, clearly this represents two very dense communities with very little interactions in between. If P and Q are the same, then there is no interesting community structure, right? This is just a so-called Erdős-Rényi graph, which is a version of this random model without any community structure. And now with this generative model, I can now ask a learning question, right? Which is, I grab this model that I drew, I jumble all the nodes together, I take away the colors, and now I ask you, can you recover the labels? It's now a very precisely formulated learning or statistical inference or inverse problem question. And of course, you're never going to be able to tell which one is blue, which one is red, right? Because there was no difference in the model. If I could have painted them green and right, I could have swapped the colors. There was no difference. But I could ask you, can you find the partition? Right? So now this is it's a very precise mathematical question. It's definitely something that one can just sit down and try to study. Right? And what would be the natural algorithm to try to recover the labels? Let's say that we do not care about computation. What would be the most natural thing? Would be, well, I look for the even splitting of the graph that has the least number of edges in between. Right? This is a very natural thing to try. So if I do this is called the minimum bisection of a graph. You try to work out when is it that this works. And you can show that in a certain scaling of the probabilities, right? Just believe me that this is the right scaling. Then if this equation is satisfied, the square root of alpha minus square root of beta is bigger than square root 2, right? Alpha is just basically P, but just scaled by sort of the right scale. The right scaling for the probability is log n over n. And so now after you do the right scaling, then if this is satisfied, square root alpha minus square root beta is bigger than square root 2, then minimum bisection coincides with the true communities. So if you're able to do minimum bisection, you recover exactly the true communities. And it's not hard to show also that if this is not satisfied, if square root alpha minus square root beta is smaller than square root 2, then actually no algorithm is able to do this. Okay? Because basically minimum bisection corresponds to the MLE and the MAP, depending on which language you use. Is sort of no algorithm in this particular problem can do better than this, or can find the true communities outside of this threshold. Okay, so now we understand. I mean, statistically speaking, we understand the problem. We know this is if we have this amount of signal, right? I'm thinking of signal as in the inner community probability being bigger than the outer community probability, sort of more signal. If you have this amount of signal, we can do it. If not, we can't. And now you can. Now, if you put your computational hat on, you say, well, okay, but minimum bisection is an NP-hard problem. Right, so minimum bisection is not an algorithm. It's not a problem that we believe there is an algorithm for that runs efficiently on all instances. And this is a problem, right? Because how are you going to then find communities, right? I mean, it's not at all clear that that this is even useful, because you will not be able to run an algorithm that takes exponential time in a large data set. And since we believe that there is no algorithm that always solves minimum bisection that is efficient, we don't expect to be able to solve it. But NP hardness is a statement about the worst case input. It's a statement about there is no algorithm that can solve all instances. But maybe the instances that I created in this generative model are actually very easy. Right? If I give you a graph without any connections, it's very easy to find the minimum bisection, for example, right? Or a complete graph is also easy, right? There's for sure many graphs that are a lot easier if they're very structured. So here I'm not exploiting like algebraic structure. I'm exploiting the fact that maybe the random distribution just makes the problem easier. And motivated by that, you can try to figure out when is it that you can actually compute minimum bisection. It's not as obvious how to answer this question, but it's also something that one can prove. That actually, if square root alpha minus square root beta is bigger than square root 2, minimum bisection can be computed efficiently. With high probability, of course. Okay, and basically you can do this by exhibiting an algorithm, like a semi-definite programming relaxation works. There's a spectral method that also works. There's many different algorithms actually that work. Okay, but the point is that actually in this regime, the regime that statistically you care about, because it's the one where you can solve the problem, actually computation is no longer an issue. Now, the fundamental question is there, like, why is this happening? Is there any fundamental reason for this to happen? Is this supposed to always happen? Right? Is this sort of happy coincidence always going to happen, or is this something special about this problem? Is there something about the fact that if the problem is statistically nice, it makes it computationally nice? I mean, it's not clear at all that computation should have anything to do with statistics. Right? And so that's the question that really drives my research at the moment, is understanding why is this happen? Is there a reason for this to happen, and when does it happen, when does it not? Okay? So let me give you some examples where we believe this does not happen. Okay? So sort of crushing the dream that this might always happen. Now,
can I ask one question?
Yeah, go ahead, of course.
I've just sent it on the chat. I'm not sure if should I
can't. I can't read it's not so easy for me to read the chat. If you could ask.
Okay, that's fine. So I'm going to respond. My question only holds for the random graph, because you started by saying that like you're drawing two random graphs, and I believe that there's other type of graphs or network, like the small world and the scale free. Can we say that this theories also hold when we have other type of network or graph, like the one that I'm saying, the small world and the scale free?
This is a very good question. I don't know. So you could there's many extensions you could try to do of this. And I agree that certain random graph models that sort of even look more like maybe real social networks, for example, right? Things like a small world graph and things of this type, or having a nice distribution over these types of graphs would be very nice. And to try to understand whether things like this happen there, I don't know. I don't know of anyone that has looked at this, although it's possible that work exists. Now you can ask questions of a different style, which is, for example, what if instead of 2 communities I make 10 or something like this? And this we know a bit more, and maybe I'll mention it later. But certainly, understanding what happens for other models of random graphs would be very interesting. In particular, models that have some geometric structure to it, and not in the sense that not every node is sort of behaving completely independent from another one, right? Like geometric graphs and so on. There's a lot of work done on those. But And so one could come up with block models for geometric graphs and things of this type. I think this is a very interesting direction for future research. And in particular, okay, let me answer, let me maybe say another couple of sentences with respect to that question, but maybe 5 slides from now, which will be easier for me to say. Yeah. Thanks for the question.
Thank you.
So, okay, so here's another example of a very simple graph model on which that we don't yet fully understand.
Afonso, one more question. Nesma asked, so the bisection method only works for 2 communities? It can't be generalized?
So if you want to say, if you want to do in more communities, then you would talk, right? The right algorithm would be a multi-section or a minimum multi-section or multi-cut or balanced cut, right? Depending on your generative model for the data, instead of the minimum bisection, you would likely use whatever is the maximum likelihood estimator in that case, or whatever it seems like an optimization problem that appears reasonable in that case, which oftentimes corresponds to maximum likelihood estimator. Okay. Maybe I'll say a few more words about multiple communities in a second.
Okay, cool.
Okay, thanks. Yeah, thanks for the question. They're all very good questions, and yeah, it's nice to especially in the online format. It's very nice to have some interaction during the talk. So very much appreciated. So here's another model, right? Just to give you sort of the negative side of this story, which I think in a way is the most interesting, which is take now a different random graph model on which you draw just what we call a Nerdish-Renyi graph. So you have n nodes, and every pair of nodes is connected with probability half. Okay? All independent. So it's like uniformly from all graphs or something like this, right? So to think of maybe the simplest graph model. Okay, now I'm going to draw another one which has a hidden clique in it. Okay, so I draw the exact same thing. So g and a half. Every pair of nodes gets an edge with probability half. Everything independent. But now there's a number k, and what I do is I pick k nodes at random, okay? And now on these k nodes, I draw a clique. So a clique is just I connect every single node in this subset of k nodes. Okay, and think of k as being reasonably large. Okay, and now I ask, can you tell these 2 graphs apart? Right, so of course, the natural way to tell these 2 graphs apart would be to go and look at what the largest clique is, because you know that one of them I added a big clique. It's not so difficult. I mean, you need to sit down and work it out. It's not trivial, but it's not so difficult to see that the size of the largest clique on the graph on the left is typically around 2 log n. Okay? Right? It's not at all trivial to just see, but it's not a very difficult calculation. And on the other hand, if k is large, of course, the largest clique on the right is going to be k, right? And it's also not hard to see. Certainly, it could potentially be bigger than k, of course, but in fact, it's not hard to see that right. K is sort of the right number, but in particular, there is a k clique for sure. So what does this tell me? That if k is bigger than 2 log n, then for sure the graph on the right looks very different than the graph on the left. In particular, if I compute the largest clique, it will be k on the right, and it'll be around 2 log n on the left. And so now I can ask, for which value of k can I tell these 2 graphs apart? Right? And the answer should be, if k is bigger than 2 log n, you should be able to tell them apart. Right? I mean, there may be lower order terms here, but I'm saying in sort of big, up to lower order terms. Now, if you go look at efficient algorithms, there's this very nice work of Nogalon, Krivoleschis, and Benisurakov from around 20 years ago, where they showed an algorithm that works when k is bigger or equal than square root n. Okay? So this is much, much bigger than 2 log n. If you do a little bit of analysis on this problem, and again, you would need to sit down and look, or maybe I would have to take 5 minutes to explain this analysis. But it's not so hard to see that at this root n size, it's actually, you start adding so many edges, there's sort of the degrees of the nodes and the number of edges and things like this start giving away the fact that you did something to the graph. Okay, so the problem gets like considerably easier at this root n size. But there's a big, big gap between 2 log n and root n. there's been no improvement since. It's been, what, 22 years? In fact, this is believed to be hard. So it's believed to be difficult to do anything better than square root n. Sort of, we as a community believe so strongly that this is hard that this is even used as a reduction primitive. So what I mean by this, I mean that people even say, oh, this other problem is difficult because if you could solve that one, then you could beat this algorithm of Alon, Krivelevich, and Sudakov, and we don't think that that's possible. Okay, and this has been successfully used to argue that other things are also difficult. Okay, so what this suggests, that there's what I'm calling the statistical-to-computational gap hypothesis. Okay? That when you're looking at a learning problem, of course, these are very idealized learning problems, right? But these are the ones that we should study first mathematically. Right? That there's sort of more than two regimes. That if you have very little signal, so the signal here would be the size of the clique that you plant. Right? If you have very, very little signal, say if k is smaller than 2 log n, then there's just no hope. Right? Of course, here it could be that there would be a hope because maybe you add another clique and there aren't that many cliques of size 2 log n, but this won't be the case, right? But in fact, if k is sufficiently small, there's just no way to distinguish the two models. And so maybe problems have this behavior that, below a certain level of signal, what I call signal-to-noise ratio, SNR, the problem is just impossible. Above another one, which here would be square root n, the problems become easy in the sense that they can be done with efficient algorithms. And in the middle, we don't know what's going on, right? Maybe we just haven't been clever enough with finding an algorithm. But I would like to argue that maybe what goes on is that there's a hard phase in this problem. Right, that some of these problems, they're somewhere in the middle where there is enough signal in the data for you to be able to solve it, but there is no polynomial efficient time algorithm that can solve it with high probability. Right? And I would argue even further that if we want to understand learning in a modern way, we should really focus on this computational threshold and not as much on the statistical one. While most of our techniques work is for the statistical one, right? Because most of our techniques work by quantifying how much information you gain, how much information you give, and things like this. And it's quite difficult to be able to do those things from a computational limited viewpoint, or how much information you can get with a computationally bounded machine, say, right? It's not quite clear how to argue about this. And so I would argue that we've spent very successfully we've developed very good tools to detect, to understand these statistical thresholds, but we really ought to focus now in understanding these computational ones, right? And understand if they are fundamental and not, and for different problems to understand where they are. Okay, and so maybe I can say now another sentence related to one of the questions. So my main interest, yeah.
Can I ask a quick question?
Yeah.
Would this be analogous to the random construction versus deterministic construction setup of some of the things we know in compressed sensing, for instance? Random matrices, like binary matrices. You have random construction that you can control, let's say, expander graphs that have a certain statistical threshold, but in the deterministic one is much worse than that. Is that analogous?
There's a different issue. Yeah, there's a different issue of de-randomization and the finding hay in a haystack type problems, right? Like building deterministic RIP matrices seems very difficult, and say and there's many things that building a random model is much easier than a deterministic one. So I can in the end maybe connect a little bit with this. But it's not completely obvious that this is exactly the same phenomenon.
I see,
right? So now there is one way in which they're very connected. But okay, I guess maybe I should say a couple of things. One is you can come up with, I focused here on graphs to be something maybe easier to see, but all that I'm saying over graphs, there's examples looking very much like compressed sensing type problems, or like principal component analysis and spike models in matrices and so on, and actually, especially the spike models in random matrices are very connected with the graph versions of the problems. If I have a bit of time, maybe I'll describe how in a second, like things like sparse PCA and things like this. Now,
okay, no problem. Thank you.
Yeah. Now, another thing maybe that I can say is that one thing you can do, so say that you're interested in building deterministic RIP matrices, for example, right? And we know that building them randomly is very easy. But one thing you could try to do is to build a random matrix, right? And then try to certify that it is actually RIP, right? Or that satisfies, for those who don't know, is a property that matrices satisfy that is nice for compressed sensing. Doesn't matter what the property is. And checking if a matrix satisfies RIP is in general NP hard. But you can now ask the question, I draw a Gaussian matrix. Is it true that for a random Gaussian matrix, we believe it's still difficult to certify that a matrix is RIP or not? And actually, we have some work on determining exactly how far in sparsity we believe it can be certified efficiently or not. I don't know if I have time to go over this, but if not, then I can tell you about this offline.
Okay.
Okay. So what I'm most interested in is in understanding what is it that happens at this threshold. Like what makes a learning problem hard versus easy. And so I try to find as simple examples as possible where I can see this happening in the hope of giving me some insight of really sort of structurally or fundamentally what is happening at this threshold. Okay? So the very natural question, another way of asking what I just asked is, what makes a problem hard? Right? It's not quite, complexity theory is quite recent, right? And complexity theory in the sense of average hardness of problems where the input is random is even more recent. This is right. It's difficult. It's difficult to properly understand what makes a problem difficult versus easy. Right? Maybe if you have a precise algorithm, it's not so hard to understand when is it this algorithm works versus it doesn't. But understanding when is it that something has an efficient algorithm to solve it or not feels a lot harder. And so there's a few heuristics or ways of trying to make, I would say, educated guesses of when is it that a problem is hard or not by proving certain structural properties of it, right? Or by arguing certain structural properties of it. So one heuristic that has been very, very successful, and I think is fascinating, trying to understand this heuristic better was part of what drove me in the research progress in the research path that I'm in today, is a connection with things in statistical physics. So the idea being, let me see if in a minute or two I can explain the main idea. If you think like a Bayesian statistician, you might say, well, I draw the blues and the reds. I then draw the graph condition on the blues on the reds by that rule that I gave of the probability P and Q. But now really what I want is the posterior distribution of the node labels given the graph. Right? This is really the object that I'm interested in. And whether the problem is possible or not amounts to whether this posterior is informative or not. But now what you have is just a probability distribution in the hypercube, right? To each node you have a plus or minus 1. So you just have a probability distribution in plus or minus 1 to the n. But this is something that physicists have been studying for a long time, right? Because you might imagine that you have like n atoms and they have maybe spin up or down, and you want to understand like magnetism or something like this. You want to understand the behavior of these plus or minus that you model as something at random with some kind of dependencies and interactions. This is actually quite similar, the type of probability distributions that you're modeling. And in fact, because statistical physicists have been doing this for quite a few decades now, they've developed very, very nice and very impressive techniques to try to understand when phase transitions on complexity of this distribution. When is it that the distribution goes from simple to complicated? Right? They're interested in understanding things. When is it that that things become magnetic or not depending on its temperature, or when is it that something becomes gas rather than liquid, or things of this style, right? But in the process, they've developed very, very nice techniques to make predictions of phase transitions on the complexity of this. And it turns out that if you go and borrow these techniques and apply it on these models, right? So effectively, you're creating like a fake physical system which corresponds to my posterior. Then the phase transitions it predicts seem to correspond exactly to where the algorithms that we know and we know how to analyze, they stop working. Right? So it seems that this notion of complexity that comes borrowed from statistical physics actually appears to say something about when is it that some problems are simple versus hard. Now, another thing you could maybe take another approach is to ask, so I'm going back now to the Clique problem. There's another very interesting phenomenon in the Clique problem, which is even if I don't plant any Clique, I can still ask the question of what is the largest Clique you can find in the graph, right? We know the largest Clique is of size roughly 2 log n. Turns out that we don't know any efficient way of finding cliques bigger than log n. And the question, one natural question is why? Is it just because our algorithms aren't so good, or is it a fundamental reason for one not to be able to do this? And one way that you might attack this problem is by trying to argue that if you look at the set of cliques of a certain size, say of size 0.9 times log n, and you look at the set of cliques of size 1.1 times log n, maybe the geometry of this set changes. Maybe it goes from something very nice and connected to something full of very far away connected components on which, if you think of an algorithm as traveling locally, it starts having a lot more obstacles, right? And so you can study the geometry of the solutions. Okay? Now, if you take sort of the first approach, you can actually argue that in a slightly different version of the community detection problem, in which you just want to detect better than random, rather than every single label, we believe that there is a computational gap for more than 5 communities, for example. And we believe, as I said, that finding a clique of size 1 plus epsilon log n in a g1/2 is hard. And many, many versions of random matrix spike models in which you have some kind of rank 1 or low rank structure added to a Gaussian matrix, we believe that they have computational gaps that we can characterize exactly where we believe they are, right? In a way that is sort of falsifiable, because we can say, I mean, not just my work, but the whole community, that we can make very, very accurate predictions of where we believe the computational gaps arise. Then we can test all sorts of algorithms against those predictions, right? And potentially find an algorithm that sort of disproves all of this, which would mean that this algorithm is doing something that we don't understand, at least from the viewpoint of these heuristics. Now, another way, so I'm running out of time, so I'll be brief. But another way to try to argue difficulty of problems is to take a more algebraic approach and to consider a certain hierarchy of algorithms that's inspired by, for those of you that know what this is, by Hilbert-Snustel-Ansatz. It's inspired basically by a real version of the Hilbert-Snustel-Ansatz problem, the so-called positive Snustel-Ansatz. Okay. Maybe a simplification of this or a related technique is by asking the following: what can we do if we restrict to using only low-degree polynomials of the data? Okay. So it turns out that it's a very nice way of modeling things, because you can basically adapt the techniques in the Neiman-Pearson lemma and so on to ask what is the possible, or ask a question that's very similar to be fully honest, of what is possible to do with the best low-degree polynomial statistical test. And it turns out that this is a computation that we can do in many examples. Right? And for example, we can say things of the type, exploiting sparsity in sparse PCA, right, where you plant a low-rank sparse structure in a random matrix, takes you a certain sub-exponential time, and we can say sort of exactly how much sub-exponential time it should take, right? And this corresponds to the best algorithms that we know. And in fact, this that I'm describing for sparse PCA, you can adapt it to say things about the certification of RIP matrices, just to go back to Boubacar's question. Okay, so if there's a certain model that I really like, which is the Sheraton-Kilpatrick-Hamiltonian model. So the idea here is, at least on the version where you just want to find the ground state, essentially what it corresponds to is I give you a Gaussian matrix, so an n by n matrix with just independent Gaussian entries, and I ask you to maximize the expression there, right? So I ask you to maximize the quadratic form over the hypercube on this. And this, we believe that there's a fundamental non-trivial, or there's a fundamental gap in certifying upper bounds for this. Okay? So if I give you the matrix, the right value for this is around, well, after you normalize by the right power of n, is around 1.5. If you, instead of optimizing over the hypercube, optimize over the sphere, right? It's like a spectral relaxation, the value is 2. Right? So this is a very easy upper bound to give. If I give you a matrix W, you can just compute its largest eigenvalue, and this will tell you something about the optimization over the sphere, and therefore be an upper bound over the hypercube. We have I would say, strong reasons to believe that doing an upper bound better than this is actually computationally hard. There's a fundamental difficulty to giving an upper bound that just doesn't correspond just to relaxing from the hypercube to the sphere. Okay, and then these ideas, I mean, after being massaged a fair amount, allow you to give computational lower bounds on certifying, you know, bounds on coloring number, on maximum k-cuts of random irregular graphs, and things of this type that I don't have time to talk about, but I'm happy to later or offline, if someone has questions, just send me an email. I'm happy to chat about this. Then, yeah, so here's the other example of basically these use essentially the same ideas. Okay, so I'm running out of time. Just to say that some of these things can be applied on problems that feel closer to real life applications, and using a certain connection between this problem of molecular imaging and algebraic invariant theory, we can actually understand what optimal reconstruction quality is, at least in sort of idealized models. And in fact, we have reasons to believe that there is a computational gap in the so-called heterogeneity problem. So when all the molecules are imaging, don't look exactly the same, which happens a lot because sometimes a protein is like open or closed or something like this. They might have different shapes, and so this is an important instance, and we believe there's a computational gap there. Okay, so I'll skip this. Then, yeah, just to say that we made, I mean, the prediction, maybe I should mention this. So for reasons that I don't have time to describe, the prediction that we got from this understanding of how many images you need to resolve a molecule was sort of very surprising from the signal or imaging processing viewpoint. But it turns out that, and so we were very surprised, but then we found a paper from 20 years ago of someone working on algorithms for these molecular reconstruction problem, and it's Fred Zigworth, and he had made this observation that from testing the algorithms and so on, he made this observation that the dependency on the signal-to-noise ratio had this strange dependency of being signal-to-noise ratio to the power 3 when the signal-to-noise ratio is very low, right? Which is yeah. So when you mathematically understand something, almost always someone a practitioner has already seen this behavior and described it. It's just sometimes not so easy for us to find it, but this time we were lucky and we found this. Yeah. Then, okay, so other methods for how you could argue hardness. Of course, the traditional thing in NP hardness is reductions, right? If X is hard, Y is hard, and you try to make a web of reductions. There's successful stories of this in the learning side, but it seems quite difficult because it's not just the problems I need to reduce to the other, but also the input distributions or the generative models. And it seems very hard to do this. And in fact, I mean, for many, many problems, I think it's fair to say we have no idea how to do this. Another thing is to look at the geometry of random optimization landscape, right? At the end of the day, what we're doing is optimizing over a random input or a function that was drawn at random, and then we're optimizing on it. So one thing one can try to understand is what the typical number of critical points or local minimum or things like this that a random function has. And there's a lot of very nice work in random geometry that answers these types of questions. Another is to restrict to certain restrictive query models like statistical query models. Right, another sort of very puzzling example is on automatic algorithm learning. Like you try to train a neural network to just solve your problem and try to understand when is it that it can learn to solve your problem or not. And in particular with graph neural networks, they say on the stochastic walk model example, they appear to behave just as well as the algorithms that we design. Although that problem, when it's sort of as that property that when it becomes easy, it really becomes easy in the sense that many algorithms work. But we don't know why graph neural networks are able to learn how to solve the problem. Right? And of course, as a mathematician, the question that really drives me is, are these all the same? Are they related? Are there implications in between them? Can we understand better how they're related? And there starts being some progress starting to make connections between some of these methods, at least in some restricted classes of problems and some pairs of these heuristics. Okay, and now of course looking ahead, I mean the big question that I sort of tried to pose is trying to understand what makes problems difficult and how we find this computational signal to noise ratio threshold. right? Whether methods are equivalent or ones are strictly more powerful than others. So this is a little different, but it's actually extremely related to what I talked about. I just don't think I have time to maybe explain why. But when is it that there's very unlikely properties in a random structure, like a random graph having just by chance a clique that's much bigger than 2 log n, that computationally I cannot detect or certify that they are not there, right? So I call this quiet properties or hidden rare events. And it's something I've spent quite a bit of time trying to understand what makes sort of a rare event be quiet in this sense. And of course, I tend to pick precise models, right? But is there a universality phenomena that if I have a Gaussian, if instead of a Gaussian it's something else, do these techniques still apply? Or even the prediction, does the prediction still apply? Can we understand that better? Right? And of course, can we find an algorithm that proves all this wrong and actually that beats all these heuristics? Right? But at least now we know what to try it against, right? But can we sort of falsify all these thresholds that we come up with? And can this help explain learning, right? Explain for us to better understand learning and supervised learning and versions of unsupervised learning. I mean, what I'm talking about is much closer in spirit to versions of unsupervised learning. Okay. Yeah, thanks so much. Very happy to take any questions. Sorry that I took the full hour. I have time. I'm happy to answer any questions.
Okay, great. Thank you very much. We are clapping, I think, at our own locations. Okay. Well, we can ask questions. The floor is open. If you have any questions, you're welcome to ask. Mohammed Al-Tat, you want to ask a question?
Yes, I'm not sure if it is a related question or not, but in the time that we live now in the data science world, the type of the network is like a dynamic. It's just keep expanding in a second. I'm not sure if your explanation was like for static deterministic graphs. What happens if we want to consider like the real world data that we have, like the social networks and something like that?
That's a very good question too. So my main focus is I think it's fair to say that my main focus is not in trying to understand the model, like problems that are as close as possible to reality, but rather to come up with problems where I've made them as simple as possible, but still there's something in it that we don't understand, right? I try to make them, try to have the things I don't understand about a problem be ideally just one, right? Because then I'm focusing really on that property. And so in particular, what I really want to understand is these, right? What makes a problem difficult versus easy. And so in that sense, I'm trying to come up with the simplest possible models on which I still don't quite understand what's going on, and I still don't quite understand what makes the problem hard, in the hope that via these problems I can develop better tools to understand when a problem is easy or hard, right? And of course, you would like to be able to say something about more closer to real world problems, but I think we're still quite far from these types of techniques being able to say something in that case. I mean, unless it's problems where so there are successful instances in the sense that there's some problems where you're the one who decides what the problem looks like in a way, right? So Boubacar mentioned compressed sensing. If you have a way of taking actually random measurements, then there's a lot of randomness in the problem that you can exploit, and this might still be close to real life. Another example is group testing, right? So that I mean has now been mentioned quite a bit because of the crisis we're currently in, right? Where you might want to test. So the original example was with, I think, light bulbs. So there are some light bulbs that are broken, and you want to know which ones are defective, which light bulbs are defective, and you might, instead of test one light bulb at a time, you might make sets of them and test. right now, the more modern justification for this problem and the potential application was with the COVID testing, right? So instead of doing COVID testings completely individual, you might make groups and make groups in a smart way, such that if you get a group, say of samples, and you say that there is at least one, say, COVID infection in this group, then for each, or there is none, right? So for each group, you might get there is at least one or there is none. Maybe if you make the groups really cleverly, and if you make enough of them, from this you can infer actually which samples were COVID infected or not to start with. And there, since you can decide the groups yourself, and you might be able to decide them randomly, actually you're quite close to these types of problems. And there's been some success stories of proposals of algorithms and random distributions on the groups for exactly this. So some work of Jakob Jalglon, for example, in Germany, and a few others that have proposed models of this type, where they really, the things we learn about random problems through this very idealized scenario can then be used if you can make real life. You can. Maybe another way to say this is, sometimes rather than making the problems you study closer to real life, you can try to make real life closer to the problems you study. Maybe this is the right way of saying, much shorter version of what I was trying to say. But just to give you a real example.
No, that's totally fine. Thanks for your presentation. It was really very interesting. Thanks a lot.
Oh, thank you.
So I have another question on the chat by Steve Kroon. Steve, you wanna explain, or I can read it? Well, he says, okay.
I was just wondering, thank you for the talk. All your examples seem to me that the source of the computational difficulty is that you're dealing with combinatorial optimization. Do you have similar examples where you got this computational statistical gap, where you've got continuous optimization, non-convex problems?
Yeah, so take, okay, so maybe I'll, can I stop sharing? And can you see my board? I think you can pin my board. I'll also describe things with words in a way that you can still understand even if you don't see it. But if you say low-rank tensor models. So there's different versions of this, but one thing you can do is say, take a vector x, say in Rn.
If you want to see the full screen, you just pin his
yeah, there's one place where you can pin mine to go.
Click on pin, yeah. And you should see the board in full.
So take a vector x in Rn, and now take the tensor, the rank 1 tensor created out of x. It can even be in 3. Already for sort of order 3 is already difficult. So what I mean by this is x outer product with x outer product with x. This is what you want to recover. And you put a certain amount of signal, right? Lambda measures how well you can, how much signal is there. And then just add, say, Gaussian noise, right? So this is Gaussian noise. By this, I mean an n by n by n random tensor where each entry is just, say, independent Gaussian. And now you can ask, for which value of lambda can you actually recover x from this measurement y? Or for which lambda can you actually tell that this has a rank 1 perturbation and is not just Gaussian noise? And I mean, in order for me to give you exactly the thresholds, I would need to spend some time normalizing, so there's no point. But the value that as lambda grows, there is definitely a believed computational and statistical SNR. So SNR stats and SNR computational. And it's even, in this case, the gap is even a polynomial in n. It's not just a constant. It's even a polynomial in n. And there's many other, if you go on tensors, there's many examples. And okay, I should say that, if I spend a bit of time normalizing things, we know sort of exactly what we believe these are. Okay. Now, but I didn't say what the norm was, what the variance, and all this. Another example of the same nature, still very continuous in spirit, is you take now, let's say let me keep in the same dimensions. Let's say I take A1 through AM Gaussian, let's say Gaussian vectors in just random vectors all in Rn, right? So I take m vectors in Rn, and now I build sort of the, okay, let me just say what it is, the Wishart version of this in a way, in which I create a tensor T that is the sum of the rank 1 tensors of these. Okay, so let's say, okay, from 1 to m. Okay, so this is three-order tensor. It's an n by n by n tensor that is rank m in this sense of rank. Right? There's many notions in rank in tensors in this sense of that's the sum of m rank 1 things. And now you can ask, of course, if m is 1, it's very easy for you to give me the AKs back. But now I can ask you, for which value of m does this start being difficult? And here we also understand this quite well. So it turns out that if m is smaller than n, then it's actually very easy, like very, very simple algorithms work. If n goes up, m can go up to something like, I think is n to the 3/2. Okay, I mean, I don't remember, I'm not 100% sure, but I think it's n to the 3/2, where we still know polynomial time algorithms that can do this. They can detect this low rank structure. While if you were able to use, exponential time algorithms, or you just want to ask if statistically there's enough information in the tensor, you should be able to go all the way to n squared. That's when, after you're in n squared, it's sort of full rank in a way, and you don't ever get to recover the things. But this is another gap that, yeah, it's not combinatorial in nature. But there's many others, even in spike models with matrices and so on. But yeah, I mean, this is a particularly nice, so this is a different kind of phenomena as this, while this is much closer in spirit to the ones I showed.
Thank you very much.
Okay. Any other question?
Hello.
Hello?
Yes, go ahead.
Yeah, sorry. I don't know if. Thank you very much for the talk. I did not.
Thank you.
I think some of the things are quite hard to understand immediately, but I just had a quick question, which I don't know if it's related to what you presented, because you mentioned sparse representations of maybe a larger, say, you have a very large network that lies in some dimension, and you have a sparse representation of that network, which is something we see often when you apply regularization to a large network. Then you have a lesser representation of that network. So the question I wanted to ask is, apart from cases where you could see people talk about overfitting and stuff like that, do we gain time if we represent these larger problems by the simpler networks, say a given sparse network? And I mean, how does somebody even show that you could gain time in this case? Because in an age where you have really large data sets or whatever, does it make sense to go in this direction when you always have to represent a larger network by a smaller one, say sparse representation? When you talk about time with respect to how the algorithm moves from the larger one to the smaller network, I don't know if this makes sense, but can we talk about time? Is time something that we can gain when we talk about this type of representations?
Yeah, so you can say, so many times, right? So this sometimes called, okay, in networks, there's very, very sophisticated ways of trying to sparsify networks or represent them in different ways and so on. But in particular, this is sometimes known in applied math as sketching, right? The idea that if you have a problem, then you can try to just sort of randomly or almost randomly project it to lower dimensions so that now your data is much, much smaller. Mm-hmm. And now because your data is much smaller, right, the computational complexity of anything on the smaller data should be a lot less, right? Because oftentimes the computational complexity of a problem depends on the size of the data, right, or the ambient dimension. I mean, this is almost always the case. And so there are instances even where you can see trade-offs between, so for example, there's a recent work by Dustin Mixon and I think a student of his and maybe a collaborator, where they see it, they investigate the following. So take the stochastic block model with two communities, like exactly the model that I described. And now put yourself far away from this critical threshold, right? So put yourself in the place where the problem is very easy. Maybe the problem is so easy that in order for you to solve it, you don't even need to use all the data. You can just sketch it in the sense of you can just pick a few of the nodes or some random sparse representation of the data, which it could even be just pick some of the nodes at random and ignore the rest. And they can show some things about this procedure and essentially show that, you know, the stronger your signal is, the more right, the more P is bigger with respect to Q, the more you can sketch. So the more information you can throw away before you solve the problem, right? And give sort of a, you know, complexity versus signal-to-noise ratio trade-off, right? The better your data is, the more you can drop some of it and work in a smaller space. And there's ways to quantify this for sure. Hope this answered the question.
Yeah. I mean, thank you very much.
Thank you.
Thank you very much. Yeah.
Yeah. Any other question? I think we should try to wrap up now. Yeah, let's thank the speaker one more time. And yeah, this has been a wonderful talk, and we're glad that you gave it to us. And I thank all of you for participating. All right, bye.
All right, thanks so much, Wakar. Thanks to everyone.
So, okay.